Hey, good morning, everyone. I'm not sure if I will have so exciting presentation as Martin had, but sorry for that. I will do my best to entertain you for the next half an hour. We'll see. So, yeah, my name is Elżbieta Ziółkowska. I'm representing the Institute of Environmental Sciences from the Jagiellonian University in Krakow. But it's working. So I want to acknowledge the whole team working together with me. So besides the team at the Jagiellonian University, that was also a big team at the Coimbra University helping. But we also, our work package on ecology and environmental drivers, which my talk is referring to, was very tightly connected with work package 5. So these two guys from the Aarhus University are also here. So this will be a bit different story because this will be a story about the landscapes and about the environment and how this environment and the landscape influences the resources which are available for bees. So as you see, so we are here at the Rich Palace Hotel. You see the beautiful surrounding of our hotel. We see the Lake Bled, but we see a lot of other features around. And then if we zoom in a bit, we start to see these small features which are very important for many animals living in this area. We see some small patches of woodland, we see some hedgerows, we see fields with different crop types. And all this complicated structure are potentially influencing the animals living in this area, also the pollinators and what is available for them. And then imagine that you would like to have your beehive somewhere there located. And the natural question would be, is that a good place for the beehive? Are the resources around supporting my beehive or not? And how this structure could influence my bees through the year. So those type of questions were driving our research in work package. So I will start with this nice simulation where you see for some exemplary landscape in Belgium, in Merendry area, how the resources on the left side, nectar, on the right side, pollen, are changing through the year. The brighter the color you see, the more resources are there. This is the area where we had a mini apiary in our big project. So it's a real study case which I'm showing you here. So now how we ended up with this beautiful simulation. So what we've done to be able to show in space and time the variability of resources which are there for bees. And of course, besides looking through the space and time, we would like the interesting question is how much in total also is available through the year. Here you see an image showing the total available pollen for 10 by 10 kilometer study area. But before I will go into details, showing you step by step how we went from some databases into these beautiful simulations, the important question is to understand how important our models actually are. Dirk talked a lot about the decrease in pollinators that we are all observing in the last decades. And one of the major or important drivers which is responsible for that is what we observe, the changes in the landscape structure. So the decrease in the grasslands, decreasing some small features in the landscapes like hedgerows, field margins, and so on. So our landscapes are changing, and the question is if they are changing in a good way to support pollinators and to support also other beneficial organisms living in these landscapes. The other important thing is, as you all know, these adequate nectar and pollen resources are crucial for the healthy status of our bees. So it is really important that not only the quantity, but also the quality of the resources which are there. And there are a lot of studies showing that the pollen quality and diversity impacts the immune response of honeybees. So it's really important. And lastly, but not least, the mapping of floral resources. So knowing how they are distributed through space and through time, this could help us identify and understand and prevent what we call hunger gaps, so where the food supply is not meeting the pollinators' demand. So we want to know when this happens. We probably want to predict it and avoid if possible. So we would like to manage our landscape in such a way to help our pollinators, and to, of course, also drive the attention of landscape managers to this important issue. So we all do that because we want to improve our beekeeping. The other very important reason is for this our development of our floral resource models, is the environmental risk assessment in honeybees. In May 2021, EFSA, so the European Food Security Authority, published a document on a new system-based approach to environmental assessment in honeybees to multiple stressors. So they acknowledge the fact that the bees, they are exposed to multiple stressors, and they are flying, they are present in the landscape in different places. This landscape is complex, and then they can be there are these multiple stressors working on them in space and time. So we have the environmental drivers, of course, but also biological agents. We have pesticides, which are also changing in space and time. And this is a very complex system, which is really difficult to understand. So within this concept of the system-based approach, there is a modeling part of this, which is called AP-SRAM, honeybee colony model. You will hear a bit more about that in the next presentation. But just to say that this is a system which allows for specially explicit individual-based modeling. Oh, sorry. Which means that each individual bee in the colony is modeled and is interacting to the environment, simulation environment. And our floral resources models are, of course, part of this modeling environment. So you can imagine this as a bit as a computer game. So we have a bee, it is flying in a simulated landscape, and there are things happening there. In case of our floral resource models, we are changing what is available there with 1 day time step, and the special resolution of our models is 1 square meter. So we are very detailed, and we are providing this detailed environment for this AP-SRAM colony model. But it is also important to say that the AP-SRAM is not the only model that is using the floral resource models that we have developed. Within the ALMAS modeling system, so it is animal, man, and landscape simulation system. Within this whole system, besides the AP-SRAM, so the model for the honeybee colony, we also have a model for solitary bee, Osmia bicornis, and also a model for bumblebee. And they all need this very detailed modeling environment to be able to work. So we are thinking, and providing this modeling environment for many pollinator models. So now something about how we went from information from single plants to this landscape level assessment. Let's go back for a moment to this to a landscape. Okay, so now you see we are not anymore in Belgium. This is landscape in Poland, and you see a land use map of a small portion of this landscape. So not the whole one, but just a part. And then again, imagine that we want to have a beehive somewhere there, and we look up what kind of resources we have around. So I marked 2 polygons on this land use land cover map for you. One is with a grassland, and another one is arable field. And as you see, as you can imagine, the floral resources which are available for bees in these 2 polygons are completely different. So of course the area is different, but also the amount of resources, the quality of resources, and the time frame through which these resources are available. So the oilseed rape field is giving a lot of resources, but only it's a short time when it's available for pollinators. In the grasslands, we have different species. The quality and quantity of resources is changing through the year, and possibly it is spanning to do the whole season. So very different, but somehow we would like to quantify both type of resources which I just explained. So what we've done, we start with, of course, with the mapping exercise. So the first thing you need is the map of the landscape elements and also of habitat types. So you need to know where we have different type of land cover polygons and what kind of possible resources we could have there, which are important. Then the next very important step was to define the plant composition for each of these habitat types. So to have a list of different species, but not only a list, we also want to know, of course, which are useful for pollinators, especially in this case for honeybees. So which are used, which are not. Then for those which were specifically selected for the further modeling, we first of all generated floral resource models for single plants. And then we summarized that, so we scaled that up first at the habitat level and then at the landscape level. So regarding the mapping of the landscapes, we based our approach on the spatial temporal landscape representation that we already are using for some years within this ALMAS modeling environment. Some of you probably know, but just to explain to others, the ALMAS is not only covering pollinators, models for pollinators, but also other important species. So this landscape representation was existing in this simulation system already before we started our work on pollinators. So within this system, as I already mentioned, we have a land use land cover map, which is of 1 square meter resolution. So each 1 square meter is mapped. And then, as I already also said, it's spatial temporal. So it's changing through the year. We have information about different crop management, which is done within this landscape. We are implemented the models for changing the height and biomass of all the vegetation types and so on. And you can see here different snapshots of different, let's say, layers of information that you can get from the system. So, so you have a vegetation type, you have a vegetation biomass, and you see more green it is, the more biomass is there. And this is changing mostly here within the arable fields. So the crop is growing, the more biomass you have. And then we also modeled the pesticide load within the landscape. So it's very, very detailed representation of the landscape that we have within the system. But what we were lacking, of course, is this information about the variability of floral resources. So that was our task, to add this information. Also important is to say that we are developing this type of very detailed representation of landscape across Europe within different EU and not only projects. So we are really lucky to have this opportunity. It all started in Denmark with Chris Topping's team. But then we added Poland and other countries. Within the BeGood specifically, we were working on UK and on Belgium. So this very detailed landscape mapping was done for these 2 countries. So we are now able to basically select any area. Normally we do it for areas 10 by 10 square kilometer, but that's not obligatory. But any type of area of a certain size and simulate the landscape in this area within the countries that are shown on this map. We are using various input data sets to build this type of landscape representations. And it's not an easy task, that I have to say. Not all the data are easily available, but it's possible. So basically, the most important, of course, is land cover and land use information, that we are merging information about arable fields which is coming from land parcel identification system that we have in Europe. We also from this system have information about how arable fields are grouped within farms. So we can model the farm units within the ALMAS system, and the different types of farm units, how they what kind of rotations they are using, how they are changing crops, how they are changing management within the farming system. We are, as I said, we are using very detailed crop management plans, which inform us what kind of management is done for the different types of crops and when. So when the pesticides are applied, when the fertilizers are applied, and so on and so forth. This is also matched with vegetation growth models, and all driven by meteorological data with 1 day time resolution. As I said, the next step, having this basic landscape mapping, was to add information about the floral resources. And first of all, we want to know what is the plant composition in the main habitat types that we have. We did it in let's say in 2 ways, because we had to differently work on natural habitat types and differently on, let's say, man-made habitat types. So for natural habitat types, that was we could use the what is called UNIS, so European Nature Information System. We use it at level 2. Here you see the map of these different habitat types at level 2 of the system. There are 45 of them. And what we started with was the information about the composition of species within these habitat types. But very soon we acknowledged the fact that we cannot really average it at the European scale, right? So we have very different composition of, let's say, coniferous forests in the north, very different in the continental zone, and very different in the southern zone. So we added to that the biogeographical regions that you can see here on the left side. The team at the Coimbra University developed something what they call bio-unis. So they add more details to this basic European nature information system. The next step was to add to that information about what kind of plants we have in different habitats. And for that, they used the European Vegetation Archive, the data from this archive. And they consist of more than 200,000 georeference vegetation plots. So people went to the field, they checked what kind of vegetation is in each plot. And the map on the left is showing you how dense this mapping exercise was. So where we have more plots which were investigated within the Europe. But based on that, it was possible to assess the list of plants for each bio-unis habitat type. And also what is the coverage and what is the frequency, so how common they are in different habitat types. And for each of these bio-unis habitat types, we characterize it by a list of, as I said, list of plant species, their frequency and coverage. In total, it included more than 8,000 plant species. And of course, this was before excluding those which are not important for bees. So don't worry, we didn't end up with 8,000 species for modeling. But here you have an example. This is for continental coniferous woodland. Separately, the composition for trees and bushes and other plants, so herbaceous plants. And for each of these bio-unis habitat types, we could create such nice graphs. The other thing was with man-made habitat types that is not included in UNI's habitat classification. So we had to really dig into the literature. We had to contact people to be able to define these compositions, because within the ALMA system we have habitat types like hedgerow or field margin along a certain field size. We have road verges, so very detailed structures, which are of course very important for pollinators. So based on the literature data, we were able to generate such plant compositions for each of these habitat types. The next step was, of course, to define the list of plants, final list of plants for modeling. Of course, taking into account the fact which are really important for pollinators and for honeybees. So for that purpose, again, the team at the Coimbra University, they developed what they called bee-friendliness plant species value. So, so each plant was actually ranked according to the friendliness to the bees. And this friendliness was based on pollen, nectar, and honeydew production, but also on flower traits, on flower morphotypes, and on pollinator interactions. There was also a lot of surveys done within the beekeepers to ask what they, from the experience, what kind of plants are most important for the bees. And this information, so this bee-friendliness value, was integrated with the information about the species average cover and the species average occurrence, so how frequent the species is within a given habitat, and that ranked our species list in which bio-UNI's habitat type. And of course, we had to put a threshold at some point, not to have not too many species to be modeled in the end, but at the same time not to miss anything which is important. So having this list, which is around 350 currently plant species that we selected, based on the approach that I explained, we then needed to generate floral resource models for these individual plants. And we use this equation that you see from our colleagues from the Lublin University in Poland, which basically is saying that the mass of resources that is available per square meter of a given resource per day depends on the or is a result of multiplication of the number of flowers that we have in this square meter, the mass of flower resources which is produced, so pollen, mass of pollen, nectar, and sugars, and what we call blooming factor. I will explain it a bit in a moment. And we all divided by the length of flowering period in days. So we needed to have information about each of these data to be able to generate the models. So the first, the information about the amount of produced pollen and nectar per square meter of a given habitat, and also information about the flower density. That was collected in what we call database on phenology and production of pollen, nectar, and sugar. That is already published. It was published in the last year, and that was really a big job. So the first, I would say, 2 years of the project was to collect all this information, to look through the databases, to dig into really very specific literature in different languages, whatever we could do with our resources at the Jagiellonian University. And this is the result. So you see the map of, which is showing the number of recorded plant species per each country. And you see there is a lot in Poland, and that there are two reasons. We are Polish, so we were able to really found very specific literature in Polish language, but also the research on pollen and nectar production, that is very traditional thing in Poland. So we have really a lot of studies coming from 50s, 60s, 70s, very, very detailed. So that was a super, really super thing to have this information to be able to put it together. Of course, we are aware that maybe somewhere in let's say France or somewhere else, there is something that we couldn't include, but of course this database could be enlarged and can be updated, and we are already now updating it, honestly say. But we already were able to have a lot of information, but we also needed information about the flowering time, and that we gathered from different databases on phenological observation across Europe, mostly the Pan-European Phenology database. That was a great source of information, but not only. We also contacted the German meteorological office. They have a lot of information. We have information about the plant phenology for crops from the Polish research office on different cultivars. And of course, we had a lot of information also from this database. So we all put it together within this equation that I showed you. And for each plant, we were able to generate such a curve showing the production. For pollen, this is the example, but also the same for sugar and the same for nectar. So I told you about this flower blooming factor that was included. And this blooming factor is basically saying that we are dividing the whole flowering period into 3 phases: the start of flowering, the peak, and the end of flowering. And for the start and for the end of flowering, we assume that the 15% of resources is available within these 2 periods, at the start and at the end. And peak, for the peak, we have 70% of resources produced by a plant available. Of course, we know that if we'll go into the field and measure it every day, we would get a much complicated curve. But because for most of the plants, we don't have such nice sets of observations, we somehow need to be more general. And this is what people are doing in the literature, assuming this kind of division. So we follow this advice. Of course, this start and end, the length of each of these periods could of course differ, and it will differ from year to year, because the flowering in our model depends on the temperature. So the time of flowering in our models is driven for now only by temperature, and when the plant is reached a certain sum of degree days, so the specific number of degree days is accumulated, the plant starts flowering, and this curve can be adapted to the current temperature conditions. And as I said, the temporal resolution of this is 1 day. So that was done for each of these more than 300 plants, if possible, because I have to say that although we are quite good in being able to find the information on pollen and nectar and sugar production, it was much worse for these phenology models. A lot of plants are missing information about phenology, such information which is important for us to be able to generate the phenological models. But for most important, of course, we were able to do that. But then the next step was to put it all together, so all the plants within a given habitat type. And here we have an example of a fallow of age 3 to 5 years, a list of different plant species which are present in this type of habitat. And then this SGDD and EGDD, this is the start of flowering and end of flowering in growing degree days. So this is driving our models. And for each of these plants, based on information on production, we are able to generate the single models. And then we put it all together, in this case, 15 individual models merged together to have this summary curve. And that was done for each habitat type. And then knowing from the map where we have different patches of different habitat types, how big they are, we can calculate the production from each patch of a given habitat type. And in total from the whole landscape. And we can do that for each day of simulation. So this is really great because then we know how this is changing in space and time. We know how this is changing through the year. So we basically we jump from this information about individual plants towards this simulation in space and time. Of course, this is not perfect yet, as nothing it is in science, I would say, but this is a nice start, I would say. We are still trying to, at the time that we are testing this for different landscape types across Europe, we are at the same time trying to update the information that we already have, to dig a bit more again into literature, because the things are being published all the time. Sometimes you can get, this day you have no information, the next day already someone published something and you have more. So it's, I would say, also a never-ending story, because we can add this information, we can make it better, but it's already a huge job that was done within this work package to be able to have these simulations. A bit more about future perspectives. What we have developed is an online tool called Resource Calculator, which for now is dedicated to, I would say, more advanced users and researchers, and it's allowing to get these graphs by yourself. So all the databases are online, and then you can just select the location for which you would like to generate your single curves. You can select the habitat type for which you would like to summarize it. And you can also select a time span for which, for what kind of weather you would like to generate it. And also you can calculate the averages through a couple of years. And this is thanks to the European data sets on weather that are now available within the Copernicus program. For now, this is under a bit of changes, because we are now updating the current databases which are online. But of course, by the end of this month, will be all updated and available for you. The other thing is that this kind of models we can also run within the ALMA's modeling environment, but this is a bit more complicated, I would say. The next steps, we are very lucky because we've got a next project, also EU funded project, Better Bee, and we are happy because we can really continue that work. And within that project, we plan to make it more oriented towards practitioners. So it will be, we plan to have also a geoportal where you can see maps, where you can zoom in. So going from a bit more research-oriented approach to something that can be used more by practitioners. So thank you for your attention, and I'm happy to answer all the questions.
Not working, sorry.
Okay. So I noticed that the level of quality of the data varies spatially a lot depending on the input data. And then I'm thinking, if you have the output of the model and you show that to policymakers, non-scientists, they have a tendency to take model output as truth with no concept of probability or error. So I'm wondering, do you have a map of error level in the models, which or like which shows the spatial distribution of your level of confidence in the model, so that if one focuses in on a certain area, that one knows that, okay, here the prediction is more likely to be true, or with a higher level of confidence, than somewhere else where the data is lower. And also, how does that relate to the differing resolutions of the input data?
Yeah, thank you for this question. It's very important. It's very difficult to do because these errors are different at different levels of our analysis. So first of all, you have different amount of data, for example, available to calculate the flowering phenology models for flowering. For some of the plants, we have thousands of data. For some others, we have few observations. So this is the first level. The second level is that the nectar and pollen information, sometimes it's available per species. And then again, there is a lot of observation, couple of observations. Sometimes it's only at the genus level. For some plants, we have nothing. So it's very different. What we are now doing, because I have no, I would like to have a nice map showing the errors, but for now I don't see how that could be easily done. But what we are doing when we are providing these databases, then for each species, per each type of information, we are providing information about the level of confidence. So that we are doing. That's why we are also very careful with sharing this with practitioners and with policymakers yet, because it's really difficult to explain these different levels of confidence at different levels of analysis. So it's really difficult. So I agree. And as a scientist, I'm also sometimes very annoyed because I have to work with what it is. Although we have this millions of observations still for some of the plants, and you could be really surprised that some plants, we have nothing. We have nothing, and this is also our goal within the Better Bee. We will work more with the beekeepers, ask them for help with gathering some kind of information on place, so in the apiaries. So a bit of this social science, I hope will help us. We will also do more inventories within different national languages. So I hope we'll fill these gaps. And but I agree, we need to be really careful with that.
Other questions?
Thank you so much. Another very interesting talk in a row. I was wondering if in the module of the landscape structure in Apisram, there is any component that takes into account the meteorological predictions. Because as far as I know, the model that they have, something about version 5, compared to historical data, in fact, underestimates the temperature that is going to be increased in the next 40 years, underestimates the precipitation. That means that we might have changes that we are not really sure how they are going to affect the phenological conditions of the plants, because maybe the flowering period will be even shorter, maybe the viscosity of the nectar will be even higher, lower, higher. Yes, okay. So is there any prediction on any component that can take these predictions of these people into the module?
That's possible, although I think we have not tested climate predictions yet. What for now we are doing, we are using the historical records on meteorological variables. We have now these great data sets for Europe, hourly data from 1950s, thanks to Copernicus. So we are doing that, but basically you can put inside the model whatever weather you would like. So if we would like to test some future scenarios, so what happens, we can do that. We can do that, and I think actually that would be a great exercise to look at how the shifts in phenology will look like if we will test different future climate scenarios, and possibly in the future how that would impact predictions from our models. So that's, I think, something really important.
Other questions from the room? Yes. We have two inputs online as well.
Thanks a lot. It's a lot of work, really, really huge data sets, really, really interesting. If I got it well, all this data are aimed to be incorporated into a predictive model. I was also wondering whether you're planning to analyze past events, like looking at correlation between the flower availability and some colony losses estimates, or disease outbreaks, because bees may use some flowers to protect themselves from some disease also. Is there a plan as well to do that, to look in space, so at the scale of maybe an apiary, if there has been a sudden disease outbreak and it has been placed in an environment with good resource, maybe they have better chances also to be more resilient to the disease. So is there also a plan not only to look in the future, but also to look back at the data we have on epidemiology and colony losses?
We have not thought about it. Thank you. That's a very nice idea. Although what would be needed is very detailed information about the landscape structure around the certain apiaries for which we have the data about the losses. So we can easily have the weather, so we can go, let's say, back with the prediction of phenology, but then we would need to be careful to see if we, first of all, if we have already this area mapped within our system. And if we have, then if we are going to such a very detailed scale as is the apiary, then I would do some field testing if we do not miss any type of important plant resources, because we base our mapping on the national topographical databases, which are very detailed. It's 1 to 10,000 in most cases, but still you can miss something. So you can miss some individual field margins if they are narrow. You can miss some hedgerows if they are narrow. So this kind of mapping within these topographical databases is not perfect. And also it is done for a certain time. So also this could miss some small changes in the landscape structure. So possibly yes, but I would say with some carefulness.
So from online, two inputs. The first one is from Cédric Allo from INRAE. And he says, for plant phenology data, there is an observatory with data that is shared online. So he shared that during your presentation with a link that you could use. And the second one is a question from, it says here, Herman. Maybe you can give your full name. Do you want to unmute Herman and ask your question?
Hello, can you hear me?
Yes.
Okay, great. Thanks for the talk. Yeah, so I was wondering, so my name is John Herman. I was wondering if you use the toxic endpoints as well for arthropods when you were looking at the pesticide load. I'm just wondering that because I'm currently doing something similar, and this could help to get a better estimate of the effects of the products on the bees that are applied in the landscape.
I think that this is a perfect question for Xiaodong. No, probably you will be talking about that, right, in the next presentation? No, okay.
Sorry.
Yeah.
I'm Xiaodong. I'm the main developer for the AP3 model, which is the honeybee colony model funded by EFSA. And the main reason for they want to fund us is to build a model which can use for the pesticide environmental risk assessment. So these are two pieces of work in parallel. So in BeGood, we are trying to develop the resource model so we can provide the floral resource in some specific area we select for the environmental risk assessment. And in the meantime, we also working on the pesticide model. which follow the crop management in different countries and in different types of farms. So they will apply pesticide to their crops, and we also check the pesticide concentration on the landscape level. And also these two will be combined together. So the floral resource will be contaminated when the pesticide is applied to the crop area, and the crop area is with some floral resource, or afterwards, I mean, they can apply the pesticide first, but then the pesticide will stay in the plant. And when it starts to flowering, then the pollinator will also get the pesticide from the plant, and we check this, and then the honeybee will bring this contaminated resource back into the hive. We check them again in the hive, and when the bee eats this, they will be contaminated, and we check the pesticide body burden on the bees. Then use this body burden, we calculate the mortality caused by the pesticide. And also we try to link this pesticide caused mortality to other factors like the virus in the colony, and also some other stress resource like the food resource availability and the temperature. So how, if they are cold or if they are warm enough for them to have a well development. And it's a very complicated model. And tomorrow in the poster session in Colossus, we are going to, with Nuno, we are going to have a poster there to show you how the foraging model, so to connect the bees, the colony, with the floral resource developed in this project. Yeah, I hope this answers your question.